There are some elements that rigorously obey the octet rule. They never have more or less than 8 electrons around them when they're the central atom, well, anytime, but particularly when they're in the central atom of a molecule. Carbon, nitrogen, oxygen, and fluorine never, ever, ever, for our purposes, disobey the octet rule. It turns out that the octet rule is more of a suggestion for pretty much everything else. Some atoms can have an odd number of electrons around them. We won't deal with that in this class. We will see several cases where some atoms can accommodate more than 8 electrons. We call that an expanded octet. And some atoms are pretty happy to have less than an octet. We call that an incomplete octet. Now, students often ask me for a list of things that can have more than 8 valence electrons. So we don't want to go too far down that road, because just because something can have an expanded octet doesn't mean it always does. Again, just because something can have an incomplete octet doesn't mean it always will. So we're not going to give any hard and fast rules about what can or which elements do or don't have expanded or incomplete octets, and instead we're going to look at some generalities. Elements that can have an expanded octet exist in the n equals 3 or greater energy levels. In other words, their valence electrons are in the n equals 3 or higher energy level. The principal quantum number for those things is 3 or greater. Our explanation for this right now is going to be that that's because they have energetically available empty d orbitals. Now, we need to be a little bit careful about this because it's not that carbon, nitrogen, oxygen, and fluorine don't have 3d or 4d orbitals. Remember, orbitals aren't real. They're just mathematical expressions, and so we can do calculations for 3d orbitals for carbon. We can excite electrons from the ground state into 3d orbitals. What we're talking about here is that the 3d orbitals are close enough in energy to the valence electrons to be useful. And so we're going to look at things in the third period of the periodic table and down below that on the periodic table, or things that have n equals 3 or greater. And we're going to say that those things can have an expanded octet. Again, that doesn't mean they always will, but they can. In a future video, we're going to look at something called formal charge, and we'll use that as a way to kind of figure out whether it's a good idea or not a good idea to have an expanded octet. In terms of incomplete octets, the two elements that we're going to look at most commonly with incomplete octets are going to be beryllium and boron. Other things can, but these are the ones that are going to be common. Again, doesn't mean they always do have an incomplete octet, just means they often can. Let's take a look at I3-, the triiodide ion, as an example. We'll start with our valence electron count. 7 valence electrons, 4 iodine times 3 iodine atoms is 21 electrons, and then for our -1 charge, we need to add 1 more. So our overall structure must have 22 electrons. Iodine is the central atom. That was easy this time, since all of the atoms present are iodine. And we'll go ahead and connect the other two with single bonds. We just used 4 electrons, and we're down to 18 left. I'm going to go ahead and start completing octets symmetrically. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so I've used 16 of my electrons. I have 2 left. The problem, or the issue here, is that 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I've used 20. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Everybody has a complete octet already, but I still have these 2 electrons left over. This is an easy scenario for you. Those leftover electrons, whether there's 2 or 4 or whatever, will always go on the central atom of the molecule. So let me draw that again so that it looks a little bit less confusing. We're going to have 3 lone pairs of atoms on that central iodine, and 3 lone pairs of atoms on each of the outer iodines as well, and a negative charge overall. Now if we go back and do another count, we can see 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22 electrons. We do in fact have 10 electrons on that iodine central atom, but that's totally legal. And we're going to say that it's legal because iodine is below the third period of the periodic table. So these are pretty straightforward. Let's do a quick example of something with an incomplete octet. Let's do BF3. BF3 is going to have 3 electrons for bromine. Fluorine has 7 valence electrons times 3 is 21. And so our total valence electron count is 24 electrons. Boron is the central atom. I just used 6 electrons making single bonds, and so I have 18 left. You can see that we have 3 outer atoms, and so you're probably already thinking, excuse me, you're probably already thinking about the symmetry there. And so if we give each fluorine 3 lone pairs, then we get down to 0 valence electrons. And we do have an incomplete octet on the boron. Now some of you are thinking, can I not take a lone pair from a fluorine and move it in and make a double bond? Sure, you can. In the last video for this chapter, we'll start to do something called, we'll do calculations for something called formal charge. The formal charge is why we're not going to do that in this case. So for right now, I just want you to look at this as an example of something that has an incomplete octet and what it would look like. We'll talk about why that's permitted when we talk about formal charge.